In this podcast is the part one of a series of two podcasts on the introductions to acids and bases. So in part one, we're going to talk about both the Irenaeus and the Bronsted-Lowry definitions of acids and bases, and then we're going to go into the properties of acids and bases. All right, so the first theory for acids and bases is the Irenaeus theory. And this is kind of a simplistic approach to acids and bases, and it essentially says that you have an acid if it releases a hydrogen ion when it's dissolved in water. So looking at the reaction, we would start with hydrochloric acid, dissolve it in water, and we get a separation of the cations and the anions. So we'd have a proton and then a chloride ion. So anything as an acid as long as it releases a hydrogen ion in water. So the base, an Irenaeus base, will release hydroxide ions when dissolved in water. Let's look at that reaction. If I took sodium hydroxide, dissolved it in water, I would expect to get a sodium cation and a hydroxide anion. We figured out that this is fairly inaccurate, and one of the biggest reasons it's inaccurate is because a hydrogen ion doesn't actually exist by itself. It's going to readily react with that water molecule. So your hydrogen ion is going to interact with a water molecule, and it's going to form what we call this hydronium ion, that charged hydronium molecule. The other issue that we have, and this is with the definition of the base, is that not all compounds that exhibit the properties of a base actually have a hydroxide ion. And one example your book gives of this is ammonia. Ammonia doesn't have a hydroxide ion, yet it has the properties of a base. So let's look at a better definition. All right, so our currently accepted definition of acids and bases is our Bronsted-Lowry definition. So Bronsted-Lowry acid or base is classified by whether they accept an H+ or a proton, or whether they donate a proton. So Bronsted-Lowry acids are proton donors. They give up a proton, and a Bronsted-Lowry base will accept that proton. So again, as we said, the Irenaeus theory was flawed because some compounds have no H, but yet they can accept a proton. So this definition works for them. And then we find too, as is the case in ammonia, which we brought up last time, NH3, we have a lone pair of electrons. That lone pair of electrons can accept a hydrogen, creating a charge, and it can act as a base in this case. So let's look at an equation. So here we have hydrochloric acid, and we are adding it to water. In this situation, we kind of have to look at what's happening in the products in order to figure out who our acid is and who our base is. I see hydrochloric acid has changed. We only have the chloride anion at the end. That means that this hydrogen must have been given up. So this is going to be my acid because it donates a proton. This proton is donated to water. Water, if you notice over here, we form a hydronium ion. Water accepts that proton. So water is acting as a base in this situation. We are not going to talk too much about conjugates here, but what we form when your water accepts a proton is we form a conjugate acid, and when hydrochloric acid gives up that proton, we are forming a conjugate base, and we will define those terms later on in class, but for now I just kind of want you to hear them so that they sound familiar when we talk in class. All right, let's go over the properties of acids specifically first. They're going to have a sour taste. I don't recommend tasting every acid you come in contact with, but if you think about what's in your kitchen, citrus is going to be acidic. Citric acid is sour, it's acidic. Balsamic vinegar is acetic acid, also an acid, as well as carbonic acid, which is found in sodas. If you were to do a litmus test, it will turn blue litmus paper red. It's an acid. It does neutralize bases. In part 2 of this podcast, we're going to go over the reactions, and so we'll go into more detail about neutralization reactions. We can classify acids as being strong acids or weak acids. If they're a strong acid, they're going to ionize completely, and that's kind of a funny term if you haven't heard it before. It means in water, every single one of we'll use hydrochloric acid as our example, every single proton is going to separate from every single chloride anion in solution. So you're going to get complete dissociation, or they're going to separate completely. That's a characteristic of a strong acid. A weak acid only ionizes partially. So here we have acetic acid or vinegar. So when you put this in water, only a few of the acetic acids are going to give up their protons. Most of them are going to remain unchanged. All right, our properties of bases are a little different than acids. They're going to taste bitter. Not a lot of bases do you taste on a regular basis, for lack of better terms. Wow. These are some examples. Calcium carbonate is a base. It doesn't really taste too bitter because they put a lot of flavor in those Rolaids. You're not going to taste Windex, which has ammonia in it. You're also not going to taste Drano, whose active ingredient is sodium hydroxide. Please don't taste bases. It's good life lessons. If you were to do a litmus paper test, you would use red litmus paper, and a base would turn that red litmus paper blue. And it's able to neutralize acids. Again, that's a topic for part 2. We can also classify bases as being strong bases or weak bases, and just like acids, we classify them based on whether they dissociate or separate completely. So examples of strong bases would be any hydroxides of group 1A and 2A elements. So for example, group 1A has sodium in it. Sodium hydroxide will dissociate completely in water. So what you'll be left with once you add it to water is all sodium cations and all hydroxide anions. You're not going to have any intact sodium hydroxide as a compound. It ionizes completely. That's what makes it a strong base. Weak bases, just like weak acids, are going to ionize partially. So an example would be ammonia. It's not going to accept all the protons from all the water, and it's not going to completely ionize, and that makes it a weak base.